Okay, friends, it's lesson 21. Lesson 21, there are two videos for this lesson. One deals with the first derivative test, that comes first. One deals with the second derivative test, that comes second. So first derivative test first, second derivative test second. It almost makes sense if you think about it. I'd like to begin this particular screencast with the corollary 3 from our last time together. Corollary 3 says if you have a function, it's continuous on a closed interval and differentiable except maybe at the endpoints, the following thing is true. If the derivative is positive, then the function is increasing. And if the derivative is negative, then the function is decreasing. And that's true regardless of how you're increasing or how you're decreasing. If the function is increasing like so, if the function is increasing like so, doesn't matter. Derivative is positive, derivative is positive, derivative is positive, derivative is positive. If the function is decreasing, if the function is decreasing, it doesn't matter. Derivative is negative, derivative is negative, derivative is negative. That we'll pretend that touches, sure. Derivative is negative. If the derivative is positive, then the function is increasing. If the derivative is negative, then the function is decreasing. And that leads us to think about a picture that's in every calc book that's ever existed. Some picture that looks something like this. And you identify some key points, the place where this bottoms out, the place where this sort of flattens out, the place where that tops out. And we think to ourselves about the values of the derivative in these different zones across the domain. So in this zone, the derivatives are positive, the derivatives are positive, the derivatives are positive, and conveniently the function is increasing. In this zone, the derivative is negative, the derivative is negative, derivatives are negative, and in this zone, the function is decreasing. And then the derivative is positive, the derivative is positive. In this zone, the derivatives are positive, and the function is increasing. Then it flattens. There's a flat tan right here. And then on the other side of that, the derivatives are still positive. They're positive. Derivatives are positive in here, and the function is increasing. And then out here, the derivative is negative. The derivative is negative. Derivatives out here are negative, and the function is decreasing. So if we take a look near a max, let's say, we'll use magic pen. If we take a look near the max, what happens to the derivative on either side? Well, the derivative is increasing on the one side and decreasing on the other. If we go to this max over here, the derivative is positive on one side, negative on the other. The function is increasing on one side, decreasing on the other. So in both of these cases, the derivative changes from positive to negative because the function changes from increasing to decreasing. At the min, the derivative changes from negative to positive. The function changes from decreasing to increasing. But at a point like this, where the tangent is flat, but the derivative is positive on both sides, this is neither a max nor a min. And this sort of thing is chronicled for us in the first derivative test. First derivative test says if you have a continuous function and it's differentiable except maybe at the place you're worried about, then f of c is one of these things. If the derivative changes sign from positive to negative, then you have a max. If the derivative changes from negative to positive, then you have a min. And if the derivative has the same sign on both sides of c, then you don't have a max, you don't have a min. And that is completely consistent with what we just saw. If the derivative changes from positive to negative, if the derivative changes from positive to negative, the function changes from increasing to decreasing, you have a max. The function changes from increasing to decreasing, you have a max. If the derivative changes from negative to positive, then you have a min because the function changes from decreasing to increasing. This is the sort of thing you should become very, very familiar with. I will illustrate with an example or two. So let's find local max and mins for f of x equals x cubed plus 3x squared minus 24x minus 2. So where are the local max and min values? So how do we do this? Well, we look for the derivative. The derivative, f prime of x, that's 3x squared plus 6x minus 24, which factors as 3 times x minus 2 times x plus 4. And so we ask ourselves, where are the critical values? Where are the critical points, the points where the derivative is 0 or changes sign somewhere. Derivative is 0 or undefined. Well, the derivative is defined everywhere here, so we're just looking for where the derivative is 0. So we imagine for ourselves a number line. There are two special places on that number line. This is 0 if x is 2. This is 0 if x is negative 4. And so we ask ourselves, how does the sign chart look? The SIGN sign chart look? And we can know that because these are the only two places where the derivative could change sign. So whatever sign the derivative has in this area, if it has it at one place, it has it at all the places. If the derivative is positive at this point, it's positive all the way through. If it's negative at this point, it's negative all the way through. So we pick our favorite number that's less than negative 4. Go ahead, pick one, any number that's less than negative 4. Sub it in. See what happens. Sub it in. See what happens. You get a negative number times a negative number. That's a positive number. Then you take your favorite number between negative 4 and 2. Go ahead, pick one. Your favorite number between negative 4 and 2. And you sub it in. You get a negative number times a positive number. That's a negative number. Derivative is 0 here. Derivative is 0 here. You pick your favorite number bigger than 2. Go ahead, your favorite number bigger than 2. Plug it in. Plug it in. You get a positive number times a positive number. That's a positive number. So the derivative is positive, and then negative, and then positive, which means that f is increasing, and then decreasing, and then increasing. So where is there a max? Well, f has a max, a local max, at x equals negative 4 because, and we're going to give a calculus reason here, f prime changes from positive to negative at x equals negative 4. And similarly, f has a min, a local min, at x equals 2 because, and we're going to give a calculus reason here, f prime changes from negative to positive at x equals 2. We want to give a calculus reason. We want a reason that's based on the derivative. So we don't want to talk about what f is doing. We want to talk about what f prime is doing. I will illustrate with one more example. Find local max and mins for g of x equals x over x squared plus 1. So we want to know where the local maxes and mins are. And so we consider the derivative so that we can use the first derivative test. That's quotient rule. Bottom times derivative of the top minus the top times the derivative of the bottom. calc. So there it is. So what is that? Well, that's x squared minus 2x squared, and that's 1 over x squared plus 1 squared. So if we're looking for our number line, we're going to consider all the places where the derivative is 0 and all the places where the derivative does not exist. If I'm thinking about where the derivative does not exist, well, there isn't any such place because this denominator is always positive. So I look at the numerator and I ask myself where 1 minus x squared is 0, and that happens at plus or minus 1. And so those are the places on the number line. The derivative is 0 at both of those places. So now we try our favorite numbers, one that's less than -1, one that's between -1 and 1, one that's greater than 1, and we ask ourselves, what does the derivative give us at any of those places? So I'll just think for a moment and you can make sure that you confirm for yourself that this is what should be. And that means that our function goes from decreasing to increasing to decreasing. And so what does that mean? That means that g has a local max at x equals 1. Why? Because g prime changes from positive to negative at x equals 1. That's the calculus reason. G prime changes from positive to negative at x equals 1. There's a min at x equals -1 because g prime changes from negative to positive at x equals -1. Okay, so that's not the only thing for us to consider. We will soon consider the second derivative test, but that's a whole other video.